Hello and welcome to section 1.5. I'm going to talk you through the quadratic applications. This is found in your book on page 124 if you want to follow along in the book. I'll be going through the examples. The first example, I would ask you to read that, but I will read it aloud for you. But again, you may want to get to page 124 and follow along. It says a piece of machinery produces rectangular sheets of metal such that the length is 3 times the width. Equal size squares are then measuring 5 inches are cut out of the corners so that the resulting piece of metal can be shaped into an open box. So what they're going to do is cut out, so you got a rectangle, they're going to clip out the 4 corners, equal size, they're squares, and when they clip those out, then they can fold these sides up and it'll be a box. So it'll be an open top box. Alright, and then the other clue it gives us is the volume of the box is 1,435 cubic inches. So it's measured in cubic inches. So length times width times height equals the volume of a box is the formula we're going to need for this. Since it mentioned volume, volume is length times width times height. So right now we've just got a rectangle. Now it had to give us some sort of clues about this rectangle. So it did start us off with that, and it said that the length is 3 times whatever the width is. So we don't know the dimensions, but we know this is totally unknown, and then the length is 3 times that. Then the next clue is they cut out these 5-inch corners, clip those off. So now the length of the actual box is shorter than 3x. You know, abstractly it's 3x. But then we came in 5 inches here and 5 inches here that we've subtracted or cut off. So the length of the box itself is going to be 3x minus 5, which is minus 10. Then the width of the box, again, we denoted it as x originally, but then we clipped off 5 inches this way, 5 inches this way. So the actual box after the squares are clipped off is x minus 10. And so now we're almost ready to make an equation out of this volume equals length times width times height. So it did give me the volume straight up in the reading. It's 1,435 cubic inches. Now don't worry that it's measured in cubic inches. That does not mean that this number is cubed in any way. That's just the units. The units are in cubic inches because in the box it will have a length in inches, a width in inches, and a height in inches. When you multiply those 3 together, you got inch times inch times inch, or cubic inches. So the units work out, but we don't put it in the actual equation. But we do denote that these should all be in inches. And they will be in this problem. So the length of the actual box is this 3x minus 10. The width of the box is the inner dimension there, the x minus 10. Then the height is not necessarily in the reading, but you can derive it by thinking about this 5 inches you cut out. Whenever you lift that up to fold it into the box, it's going to be sitting 5 inches for its height, its tallness. So that is 5. Now that's the setup. That's the hardest thing about reading problems, right, is getting it set up. But then we have to solve it. So it is going to be a quadratic equation, as all the things on this first section 1.5 will be. So you want to try to do any tricks you know to make it easier to solve. And one thing we can do on this one is, because these are all multiplied together, we can divide out the 5. The 5 will divide evenly into this other side, and that'll reduce it down nicely. So if you see a way to reduce it, always try to do that. And it will make the problem flow a little nicer for you, but we could have solved it without dividing. So I'm going to type in 1,435 divided by 5. So now I've got 287 equals 3x minus 10 times x minus 10. Now I'm going to have to FOIL this together and try to regroup it into a quadratic. This is not set up with the zero factor property we talked about on 1.4, because you got something times something equals a number, not equal to 0. And even when I bring this across, it's not going to be in zero factor form. So I am going to have to totally regroup this. So foiling this, first, outer, outer, inner, inner, and so on. There's where I see I've got a quadratic, so I need to get it in standard form. I bring the 287 to the other side, making it equal to 0 now. Combining my like terms. and now I have a quadratic equation in standard form. Now it's a little bit of a difficult quadratic equation, I would call it, because those aren't easy numbers to deal with. I don't readily know the factors of 187, so I have to get my calculator and punch around a bit, but it will factor after much thinking and trying out values if you're doing the trial and error method. And I am going to look at the book to save a little time and see they factored it into 3x plus 11, 1x, and minus 17. We could check that out by the FOIL method. The first is the 3x squared, the outer, and the inner combined to be negative 40, and the last is negative 187. Now if you hate that factoring, you can always use the quadratic formula. A is 3, B is negative 40, and C is negative 187. Put it in the formula and reduce it all the way down. It should come out all to be rational answers. Anytime it's factorable, this was actually going to be a rational solution whenever you put it in the formula. So make sure you reduce it all the way. So our solutions then, when we set each factor equal to 0, we get two solutions as we normally do with quadratics. Negative 11/3 and positive 17. Now, so we got two answers, like I said, because quadratic second degree equations that we were solving, x squared should have two answers. But in a reading problem, sometimes one of the answers doesn't work back in the original, so you do need to check that out. And a negative answer would not make sense to what we're doing here in the real world. You know, the side of a box has to be a positive number. So the negative number we'll say is an extraneous solution. We'll mark that out. And the only viable solution is just the 17. And remember, it's in inches. So if we go back and we answer what are the dimensions of our box, that's a question. Or they could say what's the dimensions of the rectangle, which I think if we read the, read the problem again. It says find the dimensions of the original piece of metal. So always be careful to see what they want you to do with x. In this case, the original piece of metal, you know, let's take it back before we subtract off our little squares. In the original rectangle, before the squares were cut out, before it was a box, we just had x and 3x. So the width of our rectangle is what x is, 17 inches. The length is 3 times 17, which is 51. So now we can say the dimensions of the rectangle should be 17 by 51, and then the 5 would be, if they asked us how high the third dimension if we were back to doing a box. But anyway, yeah, the original rectangle though is just a rectangle, so length times width, 17 and 51 would be our answers. All right, so that's example 1. All right, so another type of quadratic application that we oftentimes see in our basic algebra books will be the Pythagorean Theorem. It leads to a lot of nice quadratic equations. So let me remind you about right triangles. In a right triangle, it is true that the sides, we call those A and B, this side squared plus this side squared will equal the hypotenuse squared. And again, we always call that longest side the hypotenuse. And then these are interchangeable sides. So what is true in any right triangle is a squared plus b squared equals c squared. All right, so if you read example 2, and I will read that too, it says a piece of property has the shape of a right triangle. The longer leg is 20 meters longer than twice the length of the shorter leg. The hypotenuse is 10 meters longer than the length of the longer leg. Find the length of those sides. So it's kind of a jumbled up thing there, but we can decipher it if we take our time, read each part, see what you want x to be. In the reading, you'll see that x would be the least thing known about, the shorter leg. It doesn't matter how you draw it, but I'm going to say that's my shorter leg. Then it says the longer leg is 20 longer than twice that. So 20 more than twice the short leg would look like that. Then the hypotenuse is 10 longer than long. Here's a long leg. It's all of that plus 10 more. So now we've got it all represented, and now we can put it into our equation. We know the truth is this squared plus this squared should equal that squared. So let's say x squared plus quantity. Now you will need to have that in a parenthesis. It's both terms combined, then squared, equals the hypotenuse. I'm going to call that 2x plus 30 squared. Now what you can't do on this, which would be so tempting to try, is say just drop the squaring, do the same thing to each part, but really that's not happening on this one. It is true you can do the same thing to each side of an equation, but square rooting, or squaring for that matter, it's not distributive. So you can't just say I'm going to square root this side, I'm going to square root this side. This side would work out okay, but because there's two terms here, you can't distribute the square root operation like you can with multiplication. So anyway, we can't use that trick. If we could, this would say A plus B equals C, and that is not true. That is not how it's stated. It would also be listed, and it's not. So you can't simply just get rid of the squaring. So it's just really a long problem because you're going to have to square all this out and regroup it. So we FOIL this. You can FOIL it by writing down 2x plus 20 times 2x plus 20 and go through your FOIL method. Or you could use the squaring pattern, which is the square of the first. That's going to be your 4x squared. These two numbers times together is 40x and double that, so that's 80x. And then the square of the last number, 400. That is exactly the same thing you get by the FOIL method. Notice first times first is that 4x squared. The last times last is the 400. Then your inner is 40x, and so is your outer. So you wind up with double of inner, outer is the same amount. So we just say double that. So again, it's square times together and double, and square is the pattern, squaring pattern, to save you a little time. But again, you can FOIL it. So doing it here on this last one, 2x plus 30 to the second, I would square the first, times these two together is 60x, double is 120x, and then square of 30 is 90. So a lot of terms going on there. Then we want to clean it up. It is a quadratic. We see we've got x squareds, a lot of x squareds. So we want to consolidate that all into standard form. So I am going to bring all the terms over to the left side. So right now I've had x squared or 4x squared. I'm going to bring over a minus 4x squared. So notice when I bring that over, those will cancel out nicely. Bring over the 120 becomes minus 120. And the 90 brought across becomes minus 90. So then we have it equal to 0, which is our goal for standard form. Okay, and now here we are with a standard form of a quadratic equation. And once we get there, you can use the quadratic formula. A is 1, B is negative 40, and C is 310. Or most of these are factorable if you want to make the effort to think of some factors of 310. Which I'm thinking 31 times 10, but that's not 41, so that's not it. So you could think, keep dividing, maybe 5 goes into 310, 15 might go into 310, and it winds up being what? Oh, that's 900. Sorry guys, I was like, that's not matching what they have in the book. So let me take you back a step because my number wasn't working there. You might remember on this, maybe you can see it on the screen. I'm not sure if I went too far over, but that's 900. When I did 30 times 30, and I just written 90 for you also, it must have, it might be off your screen too, but that should be a 900 I brought over. So, excuse me, that should be negative 500. Sorry guys. Okay, now let's see about factoring it. And I can foresee to multiply to be 500, 50 times 10 is 500. If I did x minus 50 and x plus 10, because I need to get a negative 500, that would FOIL and give the right middle term of negative 40. So that works for me. When I set each part equal to 0, I have an answer of 50 and negative 10. So x equals 50, x equals negative 10. The 50 is the only one that works back in the original. So that means the short side is 50. The long side is 2 times 50 plus 20. So we can figure out the 3 dimensions there that were requested.